Something pretty fundamental. It's about how two big ideas in physics, the Pauli Exclusion Principle and quantum entanglement, are connected. And maybe connected in a way you haven't thought about before.
Right.
You've probably heard of both. But we've got a central idea today that might just, well, flip things around a bit. The big takeaway we're exploring is this. The Pauli principle doesn't just, exist alongside entanglement. It seems like it actually generates it.
That's the core idea.
We're calling it Pauli-induced entanglement. And it's not some niche thing. It's apparently woven into all fermionic matter. Think electrons, protons, the stuff that makes up, well, everything. Your chair, stars.
Exactly. And what's really wild is why. It comes down to the math, the rules for identical particles, fermions specifically.
Okay.
The rule says their combined description, their wave function, has to be antisymmetric. And that mathematical requirement forces them into an entangled state.
So it's not like a force pushing them into entanglement.
No, not a dynamic interaction in that sense. It's more fundamental. We call it entanglement by identity.
Right.
Just because they're identical fermions, they must be entangled in this way.
Wow.
And that exchange interaction people talk about in magnetism and chemistry.
Yeah, always seemed a bit mysterious.
Well, it's not some extra force. It's really just an energy effect that pops out because you have this pre-existing entanglement, this antisymmetry requirement, combined with the normal electric repulsion, the Coulomb force.
Okay, so this is kind of a shortcut then to understanding how this deep quantum stuff shapes reality.
I think so. We can trace the path.
Right. So here's the plan. We'll start with particle identity, why quantum particles are weirdly identical. Then link that straight to Pauli's principle and how that necessitates entanglement. Then we'll see the consequences, atoms, magnets, that sort of thing, even how it's being used in quantum tech now.
Yeah, the philosophical side, too. It gets pretty deep.
Definitely. So let's start at the beginning. This idea of identity, or lack thereof.
Yes, indistinguishability. It's one of the huge breaks from classical thinking.
Like billiard balls, right. Even if they look the same, I can imagine putting a tiny scratch on one. I can track ball A and ball B. They have identities.
But electrons, no. They are absolutely perfectly identical. No hidden labels, no secret scratches. It's not just that we can't tell them apart.
It's that they can't be told apart, fundamentally.
Exactly. It's a core feature of nature. And this leads to a rule, the Symmetrization Postulate.
Okay, what's that?
It says if you have a bunch of identical particles and you mathematically swap two of them in their description, the overall description, the wave function, can only do one of two things.
Just two.
Just two. It either stays exactly the same, that's called symmetric, or it flips its sign, becomes negative, that's antisymmetric. Nothing else is allowed.
Symmetric or antisymmetric? How does a particle choose?
That's where spin comes in. And there's an amazing thing called the spin statistics theorem.
Sounds important.
Oh, it is. It's a cornerstone, really. It comes from relativistic quantum field theory. It connects a particle's intrinsic spin. It's built-in angular momentum.
Right, like spin up, spin down for electrons.
Exactly. It connects that spin to which symmetry rule it follows.
Okay, so what's the connection?
Simple rule, profound consequences. Particles with half-integer spin electrons, protons, neutrons, quarks, all the matter-building stuff, they're called fermions.
Got it. Fermions.
Their wave functions must be antisymmetric. It's mandatory.
Antisymmetric, okay. And the others?
Particles with integer spin photons, the particles of light, or whole atoms like helium-4, they're bosons.
Boson.
Their wave functions must be symmetric, always.
So this theorem isn't just sorting particles into boxes. You called it a top-down constraint. How does it shape things so much?
Well, think about it. This rule, antisymmetric for fermions, symmetric for bosons, dictates how particles can arrange themselves. It's why we have the periodic table. The structure relies entirely on electrons being fermions. It's why stars don't collapse under their own gravity. Fermion pressure holds them up. It's even why lasers work that involves bosons behaving collectively. It's a fundamental organizing principle.
Right, so let's zoom in on the fermions and that antisymmetry. This brings us back to the Pauli Exclusion Principle, the PE.
The one everyone learns in chemistry.
Yeah, no two electrons can have the same 4 quantum numbers. Simple statement, huge implications for atoms.
But here's the deeper layer. The PPP isn't really a separate rule we just add on.
Oh.
It's actually a direct result of that mandatory antisymmetry for fermions.
How does that work?
Think about it mathematically.
Yeah.
If you tried to put two identical fermions into the exact same quantum state, all quantum numbers identical,
okay,
and you apply the antisymmetry rule, meaning the wave function flip sign when you swap them. The only way to satisfy that condition is if the wave function is zero everywhere.
Zero, meaning?
Meaning zero probability of that state existing. It's physically impossible. So the state is excluded not by decree, but by the fundamental symmetry requirement.
Wow, okay, so the principle is just the antisymmetry rule in action for identical states.
Precisely.
Let's take that helium atom example you mentioned. 2 electrons. Ground state.
Perfect case. Both electrons want to be in the lowest energy level, the one's orbital. So their spatial description is the same. It's symmetric if you swap them.
Right.
But they're electrons, they're fermions. The total wave function, space and spin, must be antisymmetric.
So if the space part is symmetric.
The spin part has to be antisymmetric to make the total product antisymmetric.
And what does an antisymmetric spin part look like for 2 electrons?
It means one spin must be up, the other must be down. They're forced into what's called a spin singlet state. They cannot both be spin up or both spin down in that lowest energy orbital.
And you said this singlet state
Is a maximally entangled state, intrinsically.
entangled just because they have to obey this symmetry rule, not because they interacted in some special way.
Exactly. Their spins are perfectly anti-correlated. Measure one, you instantly know the other. This linkage isn't caused by a force, it's imposed by their identity and the rules of quantum statistics. Entanglement by identity.
That's incredible. So this principle, this consequence of antisymmetry, it's literally building the world, the architect of matter, you called it.
You could say that. It forces electrons into shells, creates chemical diversity, makes material solid. It's fundamental to structure.
Okay, let's nail down entanglement then. We know the phrase spooky action at a distance. More formally.
Formally, it's when a system of multiple particles is in a state that simply cannot be described by assigning definite states to each particle individually.
You can't just say particle 1 is doing this and particle 2 is doing that.
Nope. Their fates are intertwined. Measuring one tells you something instantly about the other, no matter the distance.
And the core idea today is that the antisymmetry rule automatically creates this.
Yes. The very mathematical form of an allowed antisymmetric wave function for 2 or more identical fermions is an entangled state. You literally cannot write it as separate independent parts.
So like if I have 2 electrons in 2 different spots or states.
Their combined antisymmetric description inherently involves terms like electron 1 here and the electron 2 there minus electron 1 there and the electron 2 here. You can't factor it out. Each electron is sort of in both places until you measure.
And this isn't entanglement from, say, a laser pulse in a lab designed to entangle them.
Correct. It's not dynamic entanglement generation. It's built-in statistical entanglement, just from being identical fermions.
So what's the Pauli principle's role again in this entanglement picture? It doesn't create it.
No, the antisymmetry requirement creates it. The Pauli principle is best thought of as a manifestation or a selection rule. It says, out of all possible ways you could imagine arranging these fermions, only the antisymmetric ones are allowed. And it turns out, all those allowed antisymmetric states are inherently entangled. Separable, non-entangled states for identical fermions are simply forbidden by the antisymmetry rule. They get excluded.
So the principle enforces the condition that leads to entanglement.
You got it. Now, for a while, people debated, is this statistical entanglement really useful? Can you, do anything with it for quantum computing or communication?
Because you can't label the electrons, right? You can't say, I'll measure Alice's electron and Bob measures his.
Exactly. That was the tricky part. But the consensus now is, yes, it's a genuine resource.
How so?
Because you can transfer this entanglement. You can take the entanglement that exists between identical electrons due to antisymmetry and map it onto something else, like the polarization of photons.
Which are distinguishable, or at least their paths are.
Right. And once it's on the photons, you can use it for standard quantum protocols.
Yeah.
So the original electron entanglement was real and resourceful.
Okay, that clarifies things. Now, let's connect this to the exchange interaction. You said it's not a new force.
Correct. It's really an energetic consequence of having the Pauli principle or antisymmetry acting together with the plain old electrostatic Coulomb force.
The repulsion between electrons.
Yeah. Think about those 2 cases for electron spins. Opposite spins, singlet antisymmetric spin part, and parallel spins, triplet symmetric spin part.
Okay.
For the total wave function to be antisymmetric, the singlet spin state must go with the symmetric spatial part. Symmetric space means the electrons are, statistically, more likely to be found closer together.
Closer together means more Coulomb repulsion, higher energy.
Exactly. Now, the triplet spin state, parallel spins, is symmetric in spin. so it must go with an antisymmetric spatial part.
Antisymmetric space means they avoid each other.
Right. They're statistically farther apart, sometimes called Pauli repulsion. It's not a force, just a statistical consequence of antisymmetry. Farther apart means less Coulomb repulsion, lower energy.
So the energy difference between the parallel spin case, lower Coulomb repulsion, and the opposite spin case, higher Coulomb repulsion, is the exchange energy.
That's precisely it. It's a spin-dependent energy shift that comes purely from combining antisymmetry and the Coulomb force.
And this is modeled somehow.
Yeah, often using the Heisenberg exchange Hamiltonian.
Yeah.
Looks like hex equals 2J S1 point S2. J is the exchange integral, basically quantifying that energy difference. S1 and S2 are the spin operators.
And the sign of J matters.
Hugely. If J is positive, the energy is lower when spins S1 and S2 are parallel, like in ferromagnets. If J is negative, energy is lower when they're anti-parallel, anti-ferromagnets.
This explains so much, like Hund's rules in chemistry, why electrons spread out in orbitals with parallel spins first.
Exactly. It minimizes that Coulomb repulsion by keeping them spatially separated via the antisymmetric spatial state forced by the parallel spins.
And ferromagnetism, the fact that magnets stick, that's this exchange effect making spins align.
Yes, in materials like iron, this exchange interaction is way stronger than any classical magnetic dipole interaction. It forces neighboring electron spins to align over large domains, creating a permanent magnet, all from antisymmetry plus Coulomb.
Amazing. So moving from understanding it to using it, how are scientists harnessing this Pauli-induced entanglement?
Well, it's becoming a key part of quantum information science. The trick is converting this statistical entanglement into forms we can easily measure and manipulate.
Like that photon example.
Yeah, exactly. The Cavalcanti protocol is a great demonstration. In a semiconductor, electrons naturally relax into the entangled spin singlet state because of Pauli.
Okay.
Then, when an electron recombines with a hole, it emits a photon. And you can arrange it so the spin entanglement of the electrons gets coherently transferred to the polarization entanglement of the emitted photons.
So you get useful entangled photons out, generated indirectly by the Pauli principle.
Precisely. It proves the resourcefulness.
We should probably clarify terms here because exchange entanglement sounds like it could mean different things.
Good point. There's entanglement by identity or statistical entanglement, the built-in kind from antisymmetry we've mostly discussed.
Yeah.
Then there's entanglement exchange or swapping. That's a quantum communication protocol, different thing.
Okay.
And then, crucially for quantum computing, there's creating entanglement via the exchange interaction, using that energy difference we talked about.
Oh, using the interaction itself as a tool.
Yes. In quantum dots, for instance, you trap individual electrons, their spins can be qubits.
The quantum bits.
Right. If you put two quantum dots close together, you can control the overlap of their electron wave functions with an electric voltage. This controls that exchange integral, J.
So you can turn the exchange interaction on and off.
Essentially, yes. You pulse the voltage for just the right amount of time, and the exchange interaction naturally evolves the two spins into an entangled state. It provides a controllable two-qubit gate.
Like the swap gate or the square root of swap.
Exactly. Swap is a fundamental entangling gate.
Yeah.
So the exchange interaction becomes your way to make qubits talk to each other and perform computations.
That's such a neat contrast. The same effect that passively creates magnetism in bulk materials is actively used, switched on and off, to compute at the quantum level.
It really shows the versatility of these fundamental quantum effects.
Now, to appreciate the fermions, we should look at the other side, the bosons. Symmetric wave functions, totally different world.
Completely different behavior. Remember, bosons like to be in the same state. There's no exclusion principle for them.
So they can all pile into the lowest energy level if they want.
Yes, exactly. This leads to bunching. If you have a source of identical bosons, like photons from a thermal lamp, they tend to arrive at a detector clumped together more often than random chance would suggest. It's the opposite of Pauli exclusion.
The Hanbury-Brown and Twiss effect, right?
That's the one. And the ultimate example is Bose-Einstein condensation, the BEC.
Where they all become one giant quantum state.
Pretty much. Cool a gas of bosons down really, really cold, near absolute zero. A huge fraction of them will suddenly drop into the single lowest energy quantum state available. They lose their individuality and behave like a single coherent quantum wave.
A macroscopic quantum object.
You can think of it that way.
But wait, even for bosons, their symmetric state. Is that also entangled?
Yes, it is. Just like antisymmetry leads to non-separable states, symmetry also leads to non-separable states. A BE is a massively entangled many-body state.
So particle indistinguishability, whether leading to symmetry or antisymmetry, is a fundamental source of quantum correlations, of entanglement.
Absolutely. It manifests differently: exclusion and exchange energy for fermions, bunching and condensation for bosons.
Yeah.
But the root cause is the same, particles being identical.
This really does start to mess with your classical intuition about, well, about everything. Identity, individuality.
It throws up huge philosophical questions. The problem of individuality is a big one. If all electrons are identical, what makes this electron distinct from that one?
Do they even have individual identities?
That's the debate. The standard view, often called the received view, is that they don't have intrinsic thisness, what philosophers call haecceity. Permuting identical particles doesn't physically change anything. The labels electron 1 and electron 2 are just useful fictions for our calculations.
So they're just instances of electronness.
Kind of, but there's a counterargument, a heterodox view. It challenges a famous philosophical idea, Leibniz's principle of the identity of indiscernibles.
Which
If two things have all the same properties, they must be the same one thing. But think about our two electrons in the helium atom singlet state. They have all the same intrinsic properties: mass, charge, spin magnitude, and even the same relational properties within that state. Yet we started by saying there were two electrons.
So indiscernible, but still two.
Exactly. It suggests maybe individuality doesn't require unique properties. Perhaps it comes from just being numerically distinct or from relations in space-time. It's a deep puzzle.
And you get this sort of feedback loop, right? Entanglement makes it hard to assign properties to individuals.
Which forces us to question what individuality means.
Which changes how we think about the entanglement itself.
Precisely. It's all interconnected. And don't forget non-locality. This Pauli-induced entanglement implies instantaneous correlations across space. How do we square that with our ideas of cause and effect happening locally?
Right. Does it mean the two entangled particles are really just one single system, even when separated?
That's one way people interpret it, as an indivisible whole.
Yeah.
It challenges our concepts of space and separateness.
And underneath it all, there's still the question. Why the Pauli principle? Why antisymmetry for fermions?
Even with the spin statistics theorem linking it to relativity, the ultimate why is still debated. Is it just a fundamental brute fact about our universe? An axiom we need for stability and structure?
Like, without it, matter wouldn't be stable, atoms wouldn't form, chemistry wouldn't happen.
The universe would be drastically different, likely unable to support complexity or life as we know it. So maybe it's just necessary, a foundational rule.
What a journey. We went from just noticing particles are identical to this rule of antisymmetry, to the Pauli principle, to inherent entanglement, to the structure of atoms, magnets, even quantum computers.
All stemming from that simple yet profound fact of identity. It really hammers home that entanglement isn't the exception for fermions, it's the default state.
So where does the research go next?
Oh, lots of directions. Refining those quantum computing protocols using exchange interactions, looking for Pauli-driven effects in more complex systems, maybe biology, maybe high-temperature superconductors.
Interesting.
And the philosophical debates continue, trying to make sense of what quantum mechanics tells us about the nature of reality and identity.
So as you finish listening, maybe take a moment. That chair you're sitting on, the screen you're looking at, the air you're breathing, it's all held together, structured, given its properties, because of this deep rule born from particle identity. It doesn't just explain everyday phenomena. It forces us to rethink what identity and existence even mean at the most fundamental level. Makes you wonder what other basic rules are out there, still waiting for us to fully grasp their implications for reality itself.